Hello everyone, I'm Hong Pan, and today please allow me to introduce our paper, Deep Neural Network with Walsh Hadamard Transform Layer for Ember Detection during a Wildfire. And so first, let's discuss what's the Ember. So Ember is like this. They are burning pieces of airborne woods and vegetations produced by wildfires. They may start new fires at wildland, and they can travel miles in the wind. They can cause wildfires to spread not only quickly, but also unpredictably. They can ignite the fire behind the fireman. And so they are very dangerous. So we need to detect them to protect everyone. Now let's discuss our layer that's based on the Walsh Hadamard transform, WHT, and discuss how we reverse resonate using it. We use the Walsh Hadamard transform to transform the signal from the time domain to the frequency domain like this. Then we scale the coefficients in the transform domain, and then we apply smooth transholding, which is our nonlinear function in the frequency domain. And finally, we apply another Walsh Hadamard transform to convert signal back. So what's the Walsh Hadamard transform? This transform is proposed by two people, Dr. Walsh and Dr. Hadamard. This transform is very similar to the fast-Fourier transform, but the coefficient is 1 and -1 instead of the e2 something. So this one is very simple. This one is a simplified version of the Fourier transform, and it's energy efficient because we can achieve it without any modification. If of course the only modification is here, the normalization. So we use this transform in this task. Now let's discuss our nonlinear function smooth transholding. So this one is a variant from the soft transholding. We change the sign to 10H. We don't usually loop because we want both positive and negative parts of the feature values in the Walsh Hadamard domain because they are equally important. Now let's discuss how we reverse resonate using our layer. So the original resonate input is W times H times C, width times height and times color channel. And our input is W times H times T. T is a time channel. Our input is in grayscale, so we don't have the color channel, but we have the T channel because we are feeding the videos. We insert an Walsh Hadamard transform layer in each resonate convolution block like this. So we insert it at the beginning, and we also apply a Walsh Hadamard transform layer at the beginning of the resonate. Because the resonate, it starts with one regular convolution, and then it follows with many convolution blocks. So we also insert one layer before it because at this moment, the input haven't been changed by any layers. So it contains the most pure information. So we use our layer to take the temporal analysis, and the spatial time analysis among the spatial axes are still done by the regular convolution. Now let's discuss our dataset. We have 4 AR videos with fire obtained using our FASMEE experiment. Pseudo colors is applied on the frames for better visualization, but because they are AR videos, so we feed the grayscale frames into the neural network to reduce the computational cost. The resolution of the video is in 480p, and the frame rate is 30 frames per second. So like this shows, we use a 64 by 64 window to extract 32 continuous frames. So this is our input. Our input is 64 by 64 by 32. We use 32 because the transform, it requires input as the integer power of 2. So we use 32 because and also because the frame rate is 30 frames per second. So the duration is about 1 second It's very long. We have generated this number of video clips with Ember collection, and this number of video clips without Ember collection in our training dataset. And also we generate many videos for the testing. So here's the example. So this shows our video slides. It's hard to show. It's hard to see the Ember from this one, but we can see from here. So you can see the Ember is very obvious, and it's very hard to see from a single frame. That's the reason we need to use the video analysis. Now let's discuss our results. So what we are doing, we compare our results with the regular ResNet. That means that we only feed with the one frame, and also we compare results that feed the temporal slice but does not apply our Walsh-Hadamard transform layer. So you can see that we have the better accuracy on ResNet 18 and ResNet 34. And also you can see from here, if we feed the temporal slice, there will be no false alarm rate. So that's why we need to use the video. Okay, now let's make a conclusion. So today we design a neural network for the Ember detection in our 5 videos, and we propose a novel neural network layer based on the Walsh-Hadamard transform for video processing. So this layer can extract the feature along the temporal axis. We rest ResNet 18 and 34 for Ember detection. Compare the original ResNet 18 and 34. Our revised networks achieves higher accuracy respectively, and higher true positive rate and lower false negative rate. So that's all for today. Thank you for your listening.